In this video, we are going to learn a bit more about machine learning, specifically clustering. Now, I'm first going to look at ACL very quickly. If I click on this option, machine learning, I see three things here: train, predict, and cluster. I spoke about train and predict in one of the webinars I did, so please follow the link that you were sent to go see that video. But train and predict work together. So I'm not going to do that now because I've already done that. We're going to do clustering in this particular video. So let's talk about machine learning. Now, machine learning, I must tell you, is not something that we actually have in ACL. I know Galvanize called it machine learning, but that is not actually correct. They heard this word and thought it might sound cool from a marketing point of view, but it is not true machine learning. So train and predict are not true machine learning, and clustering, which we are going to do, is even less so an example of machine learning. So what is machine learning actually? Well, it's when a machine learns to do something. For example, Garry Kasparov, the chess champion, played against a computer called Deep Blue many years ago, and Deep Blue basically learned how to get better at playing chess. It observed various chess players, it played against various chess players, and more recently, there was an even more advanced program that also played chess, and it learned even better than Deep Blue to play how to play chess. So basically what happens is a program that plays chess that has machine learning capability is just like a human in that it learns from its past mistakes. Plays against one player, if it loses, it tries to figure out what it did wrong, what the other player did that was clever, tries to learn from them, and so on and so forth until it gets very, very good. And then it ends up beating chess champions such as Garry Kasparov. So machine learning is where a machine actually learns in a similar fashion to the way we human beings learn. As I said, in ACL, we don't have machine learning. Even though it's called machine learning, it doesn't actually exist. Now, let's first talk about an ACL script, a normal ACL script. A normal ACL script to find ghost employees, for example, is not machine learning. So I might write a script in ACL to say, let's see which employees are in the payroll file, but not in the employee master file. That script that I teach ACL is going to be run every single month. It doesn't spot trends. It doesn't look for patterns. It does exactly what I told it to. Check who is in the payroll file, but not in the employee master file. It does not learn anything from what I told it to do. So when it finds there's a list of employees, maybe in payroll, but not in the master file, it doesn't draw conclusions. It doesn't think to itself, how do I use this next month to find more ghost employees? Can I spot some kind of a pattern here? Is there a way I can modify this ghost employees test? Can I add to it? Can I subtract from it to make it better somehow? A script doesn't do this. A script sticks to the exact instructions I taught it. The script doesn't get better, doesn't get worse unless I change it. So ACL, the script, is not learning. And this is the same script that I run month after month. It just never changes unless, of course, I change it. So ACL scripts don't learn anything. They don't improve. They don't get worse. They just stay the way I left them. And this is really what machine learning, as it's called in ACL, is like. It's the same algorithm that we use month after month after month. So you don't really learn anything new. So I know it's called machine learning in the interface, but it's not machine learning at all. So if there are clients who are savvy about machine learning, what it really is, they are going to discover that what we call machine learning in ACL is not actually machine learning. All right. So let's talk about so-called machine learning in ACL, specifically with reference to clustering. With clustering, what happens is ACL looks at data that we give it. So we might give it 10 million transactions, let's say, and then it groups those transactions together. ACL decides how to group it together. So in a sense, you could say, oh, well, ACL is using machine learning. It is learning where these groupings are. It is figuring out for itself where the groupings are. Well, that's not entirely true because it has an algorithm in the background, like a script that tells it how to do this. And that algorithm never changes. It never gets better. It never gets worse. ACL doesn't learn anything. So going forward into future months, it doesn't say, okay, in month 1, I found these groupings. So how does this impact month 2? ACL's so-called machine learning, the clustering does not work like that at all. So it's not proper machine learning. So it doesn't remember what it learned in month 1 or month 2 or month 3. It doesn't draw conclusions. It uses a simple algorithm, just like ACL would use a script I gave it to find ghost employees, the same instructions month after month after month. With clustering, this is what ACL does. There's an algorithm, a script built into the background, and it just follows the same instructions every single time you do this so-called machine learning, this clustering. Right, so the machine actually learns nothing. So please understand, ACL Galvanized called it machine learning, but it isn't actually machine learning at all. It's basically a script in the background that runs the same procedures, the same steps every single time you give it a data set. It discovers nothing new in the sense of it doesn't discover anything it can use, or it doesn't apply anything it uses to improve. It just runs an algorithm. Okay, so please understand it is not actually machine learning in the way machine learning is defined in the real IT world. Okay, so let's talk about how ACL learns, so to speak, when it comes to clustering. Okay, so ACL uses what's called k-means clustering. Now, the term k-means comes from the word mean, firstly, mean meaning an average. So somehow these clusters are created by using averages, and k refers to the number of clusters. So ACL might take the data and divide it into 10 clusters or 3 clusters or 100 clusters. So k just stands for the number of clusters that we end up getting. Right, so a group starts into k number of clusters, whatever k is. It does so partly, as I said, it uses averages, but there's more to it than just averages. It uses averages to help determine where these clusters are. And once it's got these clusters, the auditor needs to look at what ACL's grouped together, and the auditor needs to draw conclusions. So with clustering, ACL doesn't draw conclusions. It just takes data and says, I'm going to break this up into groups, into clusters. The auditor then needs to look at all the transactions in each group and say, okay, why are these in the same group? What is common that I as an auditor can see? So an example might be that an auditor has fraudulent transactions and legitimate transactions, let's say, all in the same data set. And after ACL creates these groups, it turns out that there's a group of transactions that all happened after 7 o'clock at night. And the auditor looks at this particular cluster and investigates and discovers, but all these transactions are fraudulent. So why are they all in the same cluster? Things that happened after 7 o'clock at night, why are these transactions there? Oh, because the person committing this fraud didn't want anyone to be in the office when they did this. They didn't want anyone to see what they were doing. So the auditor has to look at these clusters that ACL gives as a result and needs to figure out what it means. So ACL is not learning anything. It's just creating these clusters. And we, the auditors, have to then try and understand, what does this actually mean? All right. So let's talk about some data. I've got a number line here with just a bunch of numbers from 0 to 9. Let's pretend for the moment that what we are looking at is a street, a physical street in the real physical world. And there are different houses in the street. There's a house in location number 0. So this house is number 0. There's a house in location 1. There's a house in location 2. So the red dots are houses. There is no house in location 3 or location 4. Those are still empty stands. Location 5, there's a house, 6, 7, 8, 9. So in the street, there are houses, and there are also 2 empty stands. So I've basically taken a street in the physical world, and I've drawn it in a number line. I've used a number line to represent the street and where the houses are, and I've numbered each house. Okay, so we decide we want to maybe put up a cell phone pole. So let's suppose we work for a cell phone company, and our job is to decide where to put up a pole or a switch or something so that there is coverage for everyone in the street. If we look at the data on this number line, intuitively, we might decide, okay, we want to group it into those 2 clusters. If we had to do this manually, we might feel intuitively 0, 1, and 2, those 3 houses together should get a cell phone mast. The other should get a cell phone mast, because we don't want to put a cell phone mast where 3 and 4 are. There's nothing there. We want to put a cell phone mast somewhere in the vicinity of 0, 1, 2, so they have cell phone coverage, and somewhere in the vicinity of 5, 6, 7, 8, 9. so they can get cell phone coverage. Now, this is just our intuition based on where we see the dots are on this number line. Our intuition might turn out to be correct. Maybe those 2 clusters are where we should go and put a cell phone mast, 1 for each cluster. Maybe our intuition's wrong. But we're trying to use this idea of grouping things together to decide what to do or to find a pattern of some sort. Now, how do we do this a bit more scientifically, a bit more mathematically? So what we would do, and this is effectively what ACL is going to do, is the following. I want to know which of those houses, if these are houses, belong in which clusters, so that I know where to put the cell phone masts. What we do is we randomly choose 2 of these data points. In this case, I'm going to randomly choose 2 houses. I choose house 1 and house 2. Now, there's no reason why I chose those 2. It's just random. I could have randomly chosen 0 and 7. I could have chosen 5 and 9, 1 and 8, whatever it is. This is a random selection. So I've chosen 1 and 2. These are the centroids. These are the centroids, the central part, so to speak, of my clusters. So I'm going to now look at this and say, okay, I've got a house in position 0. Now I'm trying to think, if I look at this diagram, is this house in position 0 closer to the centroid at 1 or closer to the centroid at 2? And I see that 0 is closer to 1. So I'm going to say 0 is closer to 1. So 0 and 1 somehow belong together. If I look at 5 or 6 or 7 or 8 or 9 and I ask myself the question, are those houses closer to the centroid at 1 or the centroid at 2? The answer is they are closest to the centroid at 2. So if I were to draw based on what I've noticed here, the 2 clusters, I would end up drawing that. 1 is the centroid for one of the clusters. Remember, I randomly chose 1. And 2 is the centroid for another cluster. I randomly chose 2. So, or everything in that cluster, the only thing in that cluster, that first cluster, is the centroid 1 and the number 0, that house in position 0, because that was closest to centroid 1. Then in the second centroid, we have 5, 6, 7, 8, 9, those houses, because those were closer to the centroid that I randomly chose, centroid 2. Now, this is not the exact same cluster, or these are not the exact same clusters that I've got when I tried to do this intuitively. Let me just go back a bit. Remember, when I did this intuitively, my first cluster had 0, 1, and 2 in it, and then it was 5 to 9 for the second cluster. Here you can see the way I've done it now by randomly picking centroids is I have got the first 2 dots, only the 0 and the 1 in the first cluster, and then 2 and 5 and 6 and 7 and 8 and 9 in a big cluster. Now, I've said that this is my first attempt at finding the clusters, because we don't usually, when we use k-means clustering, we don't normally take 2 random centroids and say, right, now our clusters are as follows, and that's the end of it. We take another step. We want to make sure these clusters are accurate. We want to get them even more accurate if we can. So what we do now is a calculation. We calculate the average of the data values in each cluster. So if I look at the first cluster, I have 2 values, 0 and 1. If I take 0 and 1 and I add them up, I get 1, and I divide that by 2, I get an average of 0.5. And similarly, I can take the values in a second cluster, 2 plus 5 plus 6 plus 7 plus 8 plus 9. And if I divide that by 6, I get an average of 6.1. So now we need to remember these 2 values, 0.5 and 6.1. So there are my data points. Now notice these arrows. This first arrow points to 0.5. This one points to 6.1. What we have done is we started off that process by randomly picking the centroid. Then we threw everything into the cluster that was based on that randomly selected centroid into an average calculation. And that gives us a new centroid, 2 new centroids. So I'm going to repeat this process again, but with the 2 new centroids that we calculated. So let's just see. Does 0 belong, is 0, should I say, closer to this cluster, this centroid of 0.5, or is it closer to the centroid of 6.1? Well, it's closer to 0.5. Is 1 closer to 0.5 or closer to 6.1? 1 is closer to 0.5. Is 2 closer to 0.5 or to 6.1? It's closer to 0.5. Now notice the centroid, the value of the centroid does not have to correspond to a data value. I don't have a data point 0.5 here. There's no house at 0.5. So the centroid will not always correspond to a data value. It will in the beginning when you do it the first time because you're randomly selecting a data point as your centroid, but going forward, it might not correspond to your data point. It probably won't most of the time. All right, and similarly here, I discover by looking at this that 5, 6, 7, 8, and 9 are closer to 6.1. That's centroid. They're much further away from the centroid of 0.5. So I need to draw my clusters, my oval shapes around the data points that are closest to the relevant clusters. So this is what it now looks like. 0, 1, and 2 belong to that cluster. I've just called it cluster A because they were closer to that new centroid we calculated of 0.5 than they were to 6.1. These in cluster B, I've called this cluster B, they are closer to the centroid I calculated 6.1 than to the other centroid of 0.5. So you can see I tried a second time to get my clusters. I used my previous result that I obtained, the first result I obtained by randomly selecting centroids. I used that to now just check what I would get this time. And you'll notice these clusters look more like the ones I got when I did this the first time intuitively without any fancy calculations. Now, I wonder if I can make this even better. Maybe these clusters could be better. Maybe they could be more accurate. So let me try this calculation again. So I'm going to repeat the same process with the calculation I did when I got this to get this particular answer. So in the first cluster, I have got the values 0, 1, and 2. I add them up, I get 3. 3 divided by 3 gives me an average of 1. So 1 is going to become my new centroid. And similarly, if I add up 5, 6, 7, 8, and 9 and divide that by 5, I get a new centroid of 7. So based on the new centroid of 1 and 7, let me see, using my data points, which one goes into which cluster. And I notice that 0 is closer to the centroid of 1 than it is to the centroid of 7. Therefore, 0 is going to have to go into a cluster with 1. 2 is closer to the centroid of 1 than it is to the centroid of 7. And of course, 5, 6, 8, 9 are closer to the centroid of 7 than they are to the centroid of 1. So when I draw my clusters, I get this result. So this is now, I've tried the third time to get the clusters, and I noticed something. These clusters that I got look exactly the same as what I had earlier. Anyway, I'm going to do this. I'm going to say calculate the average of the dots in cluster 1. I get an answer of 1. And do the same for cluster 2. I get an answer of 7. So hang on. I've just noticed something. If I take the clusters I have here after my third attempt, and I try to calculate new centroids so I can try a fourth time, I actually end up getting the same centroids as earlier. I'm going to get exactly the same result if I do this a fourth time, and a fifth time, and a sixth time. So what we say is we've reached convergence. These clusters are not going to shift anymore. These are my final clusters. So the idea of the centroid is you're trying to cluster things around it. It's almost like a planet, being drawn towards a star, orbiting around a star. We're trying to find out where our star is, which is our centroid. We keep shifting the centroid until such time as the data points are clustered around that centroid as closely as possible. That's how ACL learns, so to speak, where the clusters are. It uses these averages, among other things, and these centroids to calculate which things belong in which clusters. Now, as I said, ACL will give me, for example, the groupings we see in this diagram, those two clusters. But it's not going to tell me what that means. As someone who works for a cell phone company, I've got to look at this now and say, okay, what does this mean? All right, maybe it means, as I said earlier, put one cell phone mast where the houses are for 0, 1, and 2, put another cell phone mast for houses 5, 6, 7, 8, or 9. I've got to relate this now to the real world, whether it's the physical world on the ground. If I was auditing financial data, I'd need to relate this to financial data. So 0 is not necessarily the actual number of the house in the real world, but it is the number of the house that I've chosen for ACL, for clustering purposes. So I've got to have some document somewhere where I know what 0 relates to. Does it relate to a transaction from branch A? Does it relate to a house in a street? What do these things relate to? Does 0 mean something was very good or very bad? Does 0 mean something happened on a Monday and 1 means it happened on a Tuesday? I have to take whatever I have in the real world and somehow reduce it to some kind of a number, because clustering requires numbers to work. All right, so we've reached convergence. It's pointless for me using these points to try and get different clusters, assuming I want to get, of course, 2 clusters. All right, now in ACL, suppose I had data and I wanted to go and get ACL to tell me where the clusters were. This is what the screen would look like. Now I'm going to go into ACL itself shortly, but notice here, number of clusters, K value, is 2. I chose that. I said to ACL, I want 2 clusters. So ACL doesn't choose how many clusters there are. We tell it, I want 2 clusters, I want 10 clusters, I want 100 clusters. Then there's this number of iterations, maximum number of iterations. In other words, how many times must ACL try to figure out the clusters, what the clusters are, the correct clusters are. Now in my PowerPoint example, I went through it 3 times, and when I reached the 3rd time, I said, wait, I can see this is going nowhere now if I continue a 4th time. I'm finished, I've reached convergence. Here, I've told ACL in this example, only do this once, only once. Now, that's going to give me potentially an inaccurate cluster. It might be accurate, trust me, it can happen, but it might also be very inaccurate. With my PowerPoint example, my first attempt wasn't completely accurate. I had to do it more than once to get more accurate clusters. Now, number of initializations, that is, okay, let me explain it this way. I chose in my PowerPoint example 2 random points because I wanted to create 2 random clusters. Each time you want to create a cluster, you need a point. A number of initializations here, what it means isn't 2 clusters. The 2 clusters I chose there on the left. What this means is if I put a 2, ACL is going to choose 2 random points as a centroid to figure out the clusters. And once it's gone through that process, whether it's once, twice, 10 times, depending on the number of iterations I stipulated, it's going to repeat the whole thing from scratch, but it's going to choose some other random points. So it's basically, I'm saying to it, you can choose, instead of choosing just 2 random points once, the way I did in PowerPoint, choose 2 random points, see what clusters you can come up with. Now do that whole process that I did in PowerPoint again, but this time choose 2 different random clusters. And then ACL can compare afterwards which clusters, based on those random centroids I started with, actually look better to me as ACL. And it keeps only the clusters that look better. So the random centroids that are selected might actually create a set of clusters that are not that great, or a set of clusters that are really great. So we might say the number of initializations, keep trying different clusters, different random numbers to see what clusters you come up with. Okay, now this pre-processing, let's not worry about it for the moment. I'll come to it. Cluster on. Data points is the name of a numeric field. Notice this is numeric field. Now I'll show you in ACL what this looks like, because on the screen, yes, you can see the screen, but it's a bit tricky to understand what I'm talking about here. So I have a table here in ACL. I've given it the original name AR1. And here, this column called data points. Ignore those 2 for the moment. This is the column that you saw in PowerPoint. These are the numbers. There's a house in position 0, 1, 2, 5, 6, 7, 8, 9. There's no 3 or 4 because there's no house there. Remember? No house. So I decide I want to know how to cluster this, how ACL is going to group these houses, these data points together. So I go to machine learning, which, as I said, is not really machine learning, and I'm going to go to cluster. Now I want to get 2 clusters. I'll make the initializations 2, why not? And I only want to do this once. Now, as I said, it's silly to do it once, but I'm going to do it only once because I want to speed this processing up a bit for the purposes of this demonstration. I'm going to go to pre-processing, whatever that is, and I'm just going to say none. I don't want to do any pre-processing right now. We don't need to know right now what that is. And I'm going to say cluster on. So I'm going to get clusters based on which field. I want to take those data points, the 0, 1, 2, 5, etc., and break them up into clusters. And I'll create a new table. So let me call this new table. Okay, so I'm going to say K, because the K value is there. It's 2. And I'm going to say IN for initialization. I chose 2. And the number of iterations, IT, I chose 1. And pre-processing, I chose none. you don't have to give it such a silly name. Obviously, I'm just giving it this name for the purposes of this presentation. So I'm going to click OK. Now you can see here, it's busy processing. It's reading these records, and it's taking its time. Now imagine I had said, do this 100 times, repeat this process 100 times. We might, or maximum 100 times. We might be sitting here a long time. This is going to be long enough for purposes of this video. So we're just waiting for ACL to figure out in the background, using the method I showed you with the averages and the centroids, where the clusters should go. So let's just wait for this. And I feel like I'm at an airport. Let's wait. Okay. So you can see this can take a bit of time. So you don't want to run this in the middle of the day if you've chosen a large number of iterations. Anyway, so this is the result we get. Now let's try and understand what's going on here. These are the data points I gave ACL, the houses. There's a house in position 0, 1, and so on. Now these are data points as well, 1 and 7. Now what is this 1 and 7 story? Why is it repeated? Well, this is separate. Read it separately from that. Remember, in PowerPoint, when I did this clustering manually with calculations, I discovered eventually that there was a centroid in position 1 and there was another centroid in position 2. This was after trying it 3 times. So if I go here, ACL has figured out that the one centroid is in position 1 and the other is in position 7. Now if I look at my data points, because ACL thinks mathematically, how far on the number line is the number 1 from the number 1? Well, it's the same number, 0 away. Now 2 is 1 away, 3 is 2 away, 4 is 3 away, 5 is 4 away, and so on. So how far away is 1 away from 1? Okay, let's just see. 1 away from, this 1 away from 1 is 0, obviously, and 7 away from 7 is 0. Now that's not a big deal. Now see here, it says C0 and C1, cluster 0 and cluster 1. So 1 is a centroid for one cluster, 7 is a centroid for a different cluster, and ACL's called the one cluster cluster 0. I called mine cluster A, remember? And ACL calls the second cluster cluster 1. I called mine cluster B. So ACL call these things cluster C0, C1, C2, C3, depending on how many clusters I asked ACL to make for me. All right, now, in which cluster does this house 0 belong? It belongs in cluster 0. Notice when it lists the clusters here to indicate where a data point is in which cluster, it doesn't say C0, C1, it just puts the number. So this 0 is in cluster 0, this 1 is in cluster 0, this 2 is in cluster 0. So 0, 1, and 2 are in the same cluster. Look at how I did what I got when I did this manually. 0, 1, and 2 are in the same cluster. ACL called that cluster C0, right? That's cluster 0. And then 5, 6, 7, 8, and 9 are in cluster 1, C1. Look there, 5, 6, 7, 8, 9 are in 1. Now, if I look here, up here we said 1 is 0 away from 1, that's fine. But here, I'm looking at this and I think, but that's odd, because this is still 1. I mean, 1 away from, now be careful, this is the data point 1. The data point 1 is in cluster 1. So how far is it away from its centroid? How far is 1 away from 1? And I would tell you 0. But ACE's telling me, no, it's 0.131579 away. And I say to myself, okay, that's odd. That doesn't make sense because 1 is exactly 0 away from 1. So let me tell you why this answer disagrees with that answer. This answer is actually correct. First problem is fixed point arithmetic. You know ACL rounds off in a certain way. And if I'm not accurate enough, then the answer will not be accurate enough. So I should maybe, to increase the accuracy of my calculations, rather import data point 1.000, something like that. So don't call it house number 1, call it house 1.0000, something like that. To increase this accuracy, and we'll get closer to 0. Another reason it is slightly inaccurate is because of the iterations. I only did it once. If you do the iterations more than once, you find that these numbers tend to become more accurate. So it's the fixed point arithmetic and the number of iterations that decide how accurate or inaccurate these distances are. But what's most important for me is I now know which things are in which clusters. And based on that, I have now got to draw a conclusion. I have got to relate this back to the real world. What does 0 mean? What does 1 mean? What does 2 mean? In my example, these are houses. These are the positions of houses in the street. How does that, now that I know that somehow they belong in the cluster, what do I how do I use this information? Okay, I'm going to put up a cell phone mask for that cluster. So whether it's cell phone mask, financial data, something else, I have to relate back these scores that are created to where I got them from. I started with something in the real world, physically on the ground, physically in a suburb, or I started with transaction values, or I started with days of the week, or I started with times of the day. I started with something and I used numbers to represent the times of the day or the days of the week or whatever it is I'm representing. I've got to relate those numbers in those clusters back to those things and try and figure out, okay, ACL says these belong together somehow. So why? What can I as a human being spot? ACL sees them as being together mathematically, but what could I as a human being, draw? What can I see as being in common between these? Not mathematically, but what is going on? Now, let me explain to you the idea of clustering. There are certain things we know as auditors. We know, for example, that someone might like to commit fraud after working hours. We know this already. The reason we want clustering sometimes is because ACL doesn't have our knowledge and therefore doesn't have our bias about how things do work or should work in the real world. It looks at things unrelated to the way we would look at it. So it creates clusters based on what actually belongs together in some or other grouping. And those groupings might surprise us, provided we manage to draw conclusions from those groupings that we see afterwards. So ACL is saying, have you thought, you always, so ACL can't talk to us, but if it could, it might say something like, you often think about grouping the time of the day and the fraud together. Look at transactions that took place after such and such a time in the evening that's possibly fraudulent. But me, ACL, let me tell you something. I'm grouping this together by the favorite color of an employee. So let's suppose there was a tendency, people who like red commit more fraud. And now that's obviously not true, but imagine that that is what the cluster showed us. We would be surprised, but this is the point. We are learning something that we never thought of. There is a trend, there is a pattern that ACL has spotted by doing clustering without our input about how things work or shouldn't work in the real world. ACL has accidentally helped us to, well, almost accidentally helped us to discover something we never anticipated. That's the idea of clustering. So it learns where to put the clusters without our ideas about how auditing and processes and so on should work or do work. So there's none of our human bias, and it throws things out, and we might actually get the shock of our lives and go, wow, there's a pattern here I never saw. And I didn't see it before because I would never, ever have thought of looking for it. ACL found it because it has no bias. It has no preconceived ideas about how things should or shouldn't work. It just looks at the numbers. Right, so this is the idea of clustering. Anyway, excuse me. So let's get back to this. So I did that in ACL and I got a result. Now, this is the result I got in ACL when I did this for the presentation. Now notice I got the same centroids for this data, 1 and 7. Excuse me. Don't worry. Oh, excuse me again. Don't worry, I covered the microphone. You're not going to catch corona. All right. So I've got the centroids 1 and 7, which I got when I did this with you now. I showed you now in ACL what the centroids were. And notice here the distance from 0, which is in cluster 0 to centroid 1, is 0.86. And when I look here, okay, I get 0.868421. Let's just check. 868421. Okay, it's identical. All right. Now, I was hoping it wouldn't be identical, the distances. And sometimes it isn't identical. In this case, it is. At least that one is. Sometimes it's not. The reason it's sometimes not identical is because of the centroids that ACL chose the first time. If ACL chooses certain centroids, the classes might be better, worse. The centroids calculation, the centroids, will change the averages when we calculate. So it's possible that this score here might be slightly different from the score that you get when you do it in ACL. You might get a slightly different score each time. In this case, I got the same score. When I did this earlier today in ACL while preparing for this, I actually got a different score from that 0.86. But the point is they'll be similar, but they won't always be identical. Now notice also here, the heading here, it says 1 versus 3 iterations. So when I said find the clusters by going through this process of picking centroids and that only once, ACL came up with a score of 0.86 for that first one. But when I said do it 3 times, this score changed. It's becoming more accurate or potentially less accurate, okay, depending on how you want to see it. But the point is the scores are changing. As it tries to get the clusters better and better, these scores change. Again, to me, these scores aren't too important. The main things for me are which of these points are in the same cluster. Now, notice something interesting here. When I did this in ACL with you a few minutes ago, plus in this example here, with 1 iteration only, ACL actually got the clusters correct the first time. When I did it in PowerPoint, I got the clusters incorrect the first time. It was only the second or the third time that I ended up getting them correct. Now you might wonder, but how come ACL got them correct the first time? Well, it's called sheer blind luck. It chose, the centroids it chose randomly happened to take it straight to those. If it had chosen 1 and 2 randomly the way I had, and we had done this for only 1 iteration, it would not have had these clusters. The clusters would have been incorrect. They would have been different. So we got a bit lucky in this PowerPoint presentation and when I did this now in ACL, in that ACL randomly chose, good centroids, so to speak. When I randomly chose centroids in PowerPoint, I accidentally chose ones that made me repeat the process until I got to convergence. So the iterations is important because you never know at which point you're going to get convergence. Right. So here we have this beautiful number line again with these houses represented on the number line. And I said to you, 0 is closer to 1 or 7 is closer to 6, whatever it is, when we're talking about the different centroids. But we need to be more mathematical. Let's understand some of the maths. If I want to know the number 9, for example, is the number 9 closer to 1 or closer to 2? So let's suppose I randomly pick centroids. I want to start this process again. I want to randomly pick centroids, and I randomly pick 1 and 2. So I've got to decide if 9 is closer to 1 or 9 is closer to 2. So I do a calculation. 9 minus 1 gives me a difference of 8. 9 minus 2 gives me a difference of 7. Now, which difference is smaller? Oh, 7 is smaller. So in other words, 9 is closer to 2 than it is to 1. So 9 should, all things being equal, belong in a cluster with 2. This is obviously my first attempt at trying to find out where the clusters are. And I can then do the same thing, take 8 minus 2 and 8 minus 1. Here I've decided to skip some of them. So I want to know, does 5 belong in the same cluster as the centroid 2 or in the same cluster as 1? So let me do a calculation. 5 minus 2 is 3. 5 minus 1 is 4. The smaller difference is 3. Okay, so 5 belongs with 2 because the difference 3 is smaller. Fine, so 5 goes into the same cluster with the centroid 2. This is based on my first attempt at finding the clusters. Now, I need to figure out where this number 0 goes, into which cluster. Does it belong in the cluster with the centroid 1 or with the centroid 2? And I'm thinking, okay, let's see. 0 minus 1 gives me negative 1. All right, 0 minus 2 gives me negative 2. Huh? Wait, I'm confused now. A distance is a positive thing. You can't say I traveled negative 500 kilometers, not in the normal physical world. And we're not doing physics here, right? So I've got a bit of a problem. How do I now figure out if 0 is closer to 1 or closer to 2 mathematically? Because I've got negative distances and distances can't be negative. So one way I could maybe try to solve this problem is to say, I'll do my subtraction sums the normal way, but I'll take the absolute value of the answer. Now the 9 minus 1 and 9 minus 2, that's fine. Nothing will change there. Same with 5 minus 1, 5 minus 2. With 0 minus 1, if you subtract that, you get negative 1. If you take the absolute value, in other words, you make it positive, you get a 1. If you take 0 minus 2, you get minus 2, make it positive, you get a 2. So I see that the number 1 is smaller than the number 2. Therefore, 0 is closer to 1 than it is to 2. Okay, so 0 belongs in the same centroid as 1. Now, the definition of absolute value in mathematics is that if I'm taking the mod, the absolute value of x, you keep that value if x is greater than or equal to 0. If x is less than 0, then you need to multiplied by -1. So you use negative x. Now, what I've got there really isn't actually a formula. It's really two different conditions. And while it's correct, this definition of absolute value, because it's conditions and not a formula, it can make it tricky in mathematics to do calculations. It's inconvenient. So we have a trick we use in maths. What we do is we take the two numbers. So I want to know how far 9 is from 1, for example. I take the two numbers, I subtract them, 9 minus 1, and then I square it. 9 minus 1 is 8. 8 squared is 64. So by squaring it, I've made it positive. Now I take the square root of that. Square root of 64 is 8, and that's my distance from 9 to 1. Now with 0 minus 1, I get -1, but I square that, that becomes positive 1. And then I square root that to get 1. So this is a formula that I now have. Take the square root of one value minus the other squared. That's a formula I can use consistently. There's no conditions, and it gives me the same answer as absolute value would. Now, what I did there, what I've done so far in PowerPoint is I have shown you examples on one number line, houses in one street. So when you have one number line, you have one dimension. But if I have two number lines, I have two dimensions. So here we have two number lines. So we basically have a part of the Cartesian plane here. So I have 1 and 1, and this point is at 2 and 3, and this one is at 3 and 2, and so forth. Now imagine that these are houses as well, but they're not in the same street now. They're in the same neighborhood. They are in different streets, but they're in the same neighborhood. I don't want to put up a cell phone towers, so many in each street. Maybe it doesn't make engineering and financial sense to spend so much money, so many cell phone towers per street. I'd rather look at the whole neighborhood, say, okay, for this whole neighborhood, let's cluster different houses in different streets, and then I'll go find out which house I should go to. It might be in a completely different street from the other cluster, and that's where I'm going to put my cell phone masts. Now, I want to intuitively try and figure out quickly where the clusters are. And if I look at this intuitively, I think, okay, those 3 points in the bottom left-hand corner belong together, and those 5 points in the top belong together. Now, I might be right, I might be wrong. Again, clustering sometimes reveals insights, provided we analyze the clusters, that we wouldn't see. By me looking at the data like this, my clusters might be hopelessly wrong. They might be based on my human intuition, my human bias. And that's not what I want. I want ACL to do this. Now, let's do this manually, but in a more scientific, mathematical way. So let's first talk about distance between 2 points in the Cartesian plane. So I have these 2 points, and I want to work out the distance because I don't have them just on a straight line anymore. So what could do is I could draw a right angle triangle, and I could say, okay, from this point here, this coordinate here is 7 and 2. The x value here is 7. If now I have that, if I drew a point there, that point and that point on a straight line, 7 minus 3, right, will give me 4. So the length of that line, the distance of that line would be 4. The y value here is 2. The y value there is 4. This is another straight line. If I worked out the distance there, 4 minus 2 gives me 2. Now, I could use Pythagoras' theorem to say, take that, you square it, add that to that square, and take the square root to get the length of the hypotenuse. So I've got a formula to work out the length of that. So it's that difference there, that one x value minus the other x value, square the answer, add to that this y1 value, y value minus that y value, square that answer, and then square root that. So mathematically, if I wanted to get a distance formula for just a straight line, and in fact we did do it, without absolute value, I could say take the one x value minus the other one, x2 minus x1, square it, and take the square root. Now the new distance formula, at least the one for 2 dimensions, is take the 2x values, subtract them, square them, take the 2y values, subtract them, square them, add them together, Pythagoras' theorem, and then you square root that. Fine. Now, I need to figure out where the clusters are. I'm trying to do this mathematically. And step 1 is choose your centroids randomly. So I randomly selected those centroids. Now I've labeled those centroids just for the moment A and B to avoid confusion. And the other things that are serving as my data points at the moment, well, they were data points all along. I've just labeled x1, x2, x3. These are data points and they're centroids at the same time, because when you start off, you select data points randomly as your centroids. Obviously, afterwards, your centroids might not be physical data points. Right, so there are my centroids A and B. So I'm trying to figure out if X1 should go into A with a part of A, into a cluster with A, or with the centroid B. So it seems logical, do a calculation, work out the distance. I'll use that formula, the distance formula, x2 minus x1 squared plus x2 plus y2 minus y1 squared, and then square root the whole thing to calculate the distance from x1, from x1 to A and from x1 to B. And if I do that, I'll leave it to you as an exercise, but if I do that, I discover that the distance is exactly the same between x1 and A and x1 and B. They're the same distance. So now I have a problem. I'm not sure, because the distances are the same, if I should put x1 with A or x1 with B. Similarly, when I try to figure out if these points should go with A or B, I have a problem when it comes to x2. If you do a calculation, you'll discover x2 is equidistant from A and B. So should x2 be in a cluster with A or x2 in a cluster with B? So we still don't know. What ACL does is it does other calculations as well, remember. Is x3 closer to A or B? Is x5 closer to A or B? And so forth. And it turns out that x6, x5, x3, and x4 are closer to B. Now, ACL says, okay, these here are now closer to B, but I'm still not sure what to do about x2 because it's equidistant from A and B. Let's see, is x2, where is x2 close to? Oh, it's close to x3, which goes with B, and it's close to x4 and that, which goes with B. So, based on that, we'll then decide to put x2 with B in that cluster. Now, x1, does it go with A or B? Let's just see. X1, is it close to any other data points? No, those are far away. So you know what? Those are far away. Those go with B. So let me rather put it with something that doesn't go with B. Let me put it with A. So this logic happens in the background, right? So ACL ends up doing that. X1 goes with A because it's close to A and it's far away from the other things that belong with B. X2 goes with B because it's close to the other things that unambiguously belong with B. Right, so that's my first attempt. Now I need to calculate the average values again, but this is not a normal number line. We need to use that distance formula. So if I look here, x1 is in position 1 on the x-axis. This centroid that I have, the one that I chose randomly, is in position 2. 2 minus 1 gives me 1, square it, I get 1, square root it, I get 1, divide that. Sorry, what am I saying to you here? This is 1, this is 2. Okay. So the difference is 1. Okay, I think I've made a mistake in my calculation here, unless I'm wrong. Anyway, I've got it. Let's just, for the moment, say these averages are correct. Sorry, I've just lost the plot here. But you do a calculation here. Let me just maybe use the y value because I'm confusing myself here. 3 minus 1 gives me 2. And then 2 divided by 2 gives me 1. Okay, I'm not even going to do it now. Sorry, I've just lost the plot. I think I need coffee. All right, but we calculate the averages. And if you calculate the averages for cluster 1, you'll see that the x value average is 1.5 and the y value average is 2. Okay, and similarly, if you look at cluster 2 and take everything into account, all the different values, you'll see the average values are 6.5 and 1. So now we need to remember these x values and these y values when we go to the next slide. So the centroid has shifted. So if I look here, my new x value for cluster 1, or my new centroid, is 1.5 and 2. So 1.5 on the x-axis is here, and 2 on the y-axis, right? So there we have that centroid, and similarly, this here has coordinates. They just go back 6.5 and 5. Right, so 6.5 and 5. Sorry, I worked out those averages earlier today and I was able to arrive at them. Anyway, maybe I'm just no good with anything average. Okay, that's a joke. Right, so these are our centroids. So the point is we've calculated our centroids, the average x value, the average y value, and these are my new centroids. So now that we have the new centroids, what we need to do is repeat the process. Which points are closer to the new centroids? And it turns out after using the normal distance formula that x7 and x8 are closer to this centroid here, to A, and x1 is also closer to A than they are to that centroid B. So after doing all these calculations in that, we now get that those are our new clusters. Now remember, in our first attempt, we only had those 2 points, x1 and x7. They were labeled slightly differently in the one cluster together. This here was in a cluster with those. But you agree, well, intuitively anyway, that this looks better, that these things are now clustered the way they are. So we now need to try and maybe work out the averages again. And when we work out the averages again, just as I did with the one-dimension example, we end up discovering that we get the same averages, the same clusters, the same centroids. So it's not worthwhile continuing. So basically, we have now reached convergence. And I'm not saying we will always reach it after 3 attempts. I deliberately created this data because I didn't want to sit here for 20 hours going through all the different, centroids until we finally reach convergence. So it often takes a lot longer than this. Okay, please do yourself a favor, because I'm not going to do it for you right now because I've lost the plot. Go calculate those different averages, freeze the video, calculate the averages. You'll see they're correct. I've just completely lost it for the moment. I don't know why. All right. So in ACL, I decide I want to go and find out what the clusters are that these things belong to. Now, remember, I don't have just one value now on the straight line. I've got 2 sets of values. So I've got a column in ACL called data points X and data points Y. And these now, I need to choose both of those. And I can choose how many clusters I want. I can choose how many iterations I want. One is not a good idea normally, the number of initializations, and so forth. And I'm not going to do this in ACL. You've seen it before. But what I would get is something like this. This is after 1 iteration. It says, okay, you've got 2 clusters. You want a 2 cluster 0, cluster 1. The centroid for the 1 cluster has coordinates 2 and 2 and 7 and 5. And 1, 3, 2, okay, this here, point 1, 1, 3, 2, 2, 3 belong in cluster 0. So let me go look at point 1, 1 in my diagram, right? So here we have it. There's 1 and 1. It's in this first cluster, cluster 0. Let's go pick something here from this result. Over here, let's pick this one. Coordinates 7 and 4 belong in cluster 1. So let's go back a bit. 7, there it is, and 4, they belong in cluster 1, the other cluster. So you can see ACL's done in the background what I've done manually, except that I've lost the plot and ACL hasn't. It ends up getting the same answers as I did. Okay, so this is what we would see. And again, look here. The distance from this data point 1, 1 to the cluster 2, 2. It calculates this. Now, this is the distance formula in 2D in the Cartesian plane. If you calculate, you discover the answer is the square root of 2. Now, the square root of 2 is not that. The square root of 2 is roughly 1.4. Okay, square root of 2 is an irrational number. So 1.23 is not accurate, but it's not too bad. I've done it for only 1 iteration. That's the one reason it's inaccurate. And another reason is the fixed point arithmetic. Maybe when I use this data in ACL, imported it, I should have had data that said 1.000, 2.000, and so on to make these distances more accurate. But again, I'm not too stressed about that. I'm more interested in these clusters. I've got to now figure out, okay, I need to relate this 1, 1, 3, 2, 2, 3 back to the real world. So what is it that I'm looking at exactly now? Now, in my example with cell phones, this 1, 1 is the position of the house in the neighborhood. I have maybe taken a map and drawn squares on the map, and every house has a position in those squares. And now I can say, okay, based on that, I see that this part of the neighborhood needs 1 cell phone mast, that part of the neighborhood needs another cell phone mast. So I'm going to go physically in the real world. Based on this example, maybe I'll stick a cell phone mast somewhere here, stick a cell phone mast somewhere there, or anywhere in this geographical area, okay? This might, by the way, not have been an example about cell phone companies. This could have been about crime. There are houses in the neighborhood. I need to send police to patrol these neighborhoods to make sure that there's less crime. Where do I send the police? Well, based on the clusters, I should actually send a policeman to patrol here, send another someone else from the police to patrol here in that neighborhood. Of course, this is now very simplistic because have I taken into account the levels of crime in different parts of the neighborhood? If this part of the neighborhood has a lot of crime, why am I sending only 1 police officer there? I should send more than 1. So I need to think carefully about these things. I shouldn't have used two things then, you know, the location of the houses. I should have used maybe three things. The location of the houses on the map, plus the rate of crime in specific parts of the neighborhood. So I would use a three-dimensional thing then, right? Three number lines. But the point is, I've got to think carefully about what I put into ACL, because that's going to determine how meaningful or useless these clusters are. Again, it can be difficult to know what's going to be meaningful or useless, because the point of clustering is for ACL to cluster things without me being biased, introducing my bias about how things work or shouldn't work. I should be able to throw all sorts of data into ACL, and it should be able to give me clusters. And I should then look at those clusters critically and ask myself, okay, in the real world, what do they have in common, or how can I use this? All right, so mathematically, ACL would give me this, would give me those clusters. And if I do it after 3 iterations, you can see the score isn't 1.2, it's 1.3, which is closer to 1.4. 1.4 is closer to the square root of 2 than 1.3. But the clusters here are now still the same, right? Okay. Let's talk now. Okay, I want to show you only part of this video, right? Only part of it. So these are data points all over. Now this is two-dimensional, obviously. And this person, if you look here, k is equal to 5, they've decided to tell ACL to create 5 clusters. N equals 1,000 means there's 1,000 dots, 1,000 data points, 1,000 set of coordinates. And this, it hasn't done any iterations, it hasn't done anything yet. It's done it 0 times so far. So therefore, there are no groups, no clusters yet. Now, this person will obviously tell ACL if they want to do this once or twice or 10 times or 100 times. So when I play this video, you're going to see the same data points, and you're going to see the iterations as they increase. You're going to see the centroids moving, and you're going to also see the clusters forming. And at some point, this video is going to change, that N will change. They're going to introduce more data points. Just watch how the centroids move. It's a nice way to visualize kind of what is happening in the background. Okay, so let me just play this. So you can see the centroids are moving. They're there in the center of those groupings. So this person wants 10 clusters now. You can see there's more clusters. They iterated 36 times. And as with each iteration, generally speaking, they become more accurate. You can see now there's 5,000 clusters, 5,000 data points. Okay, now we are at iteration 27, 28, 29, 30. The clusters aren't really changing. At some point, you reach convergence. So we're trying to figure out mathematically which things belong in clusters. You can see with all these iterations, there comes a point where it's pointless to keep doing this. You reach convergence, right? So this is kind of what is happening in the background if we could see it visually. Right, 10,000 points, wow. And then it's trying to figure out the clusters. So it doesn't matter how many data points you have, it's going to figure out where the clusters go. All right, let me stop this video. Let me move on to the next slide. So what are these formulas in the background? For one dimension, we know what the formula is to calculate the distance between 2 points. For 2 dimensions, it's that. For 3 dimensions, you have a z-axis as well. And it will be your x value subtracted, your y value subtracted, your z value subtracted, your z-axis, right? Squared, added together, square rooted. If you have 4 dimensions, it's the same thing except that you now have, you know, a 4th bracket. If you have n dimensions, whether n is 4 or 5 or a million, you take the one value on the one axis minus the other squared, the one value minus the other on the next axis squared, and so on. Now, we human beings live in the 3rd dimension, which means we are capable of seeing things in the 1st dimension in lines. We are capable of seeing things in the 2nd dimension, like on a table. We are capable of seeing things, well, in the 3rd dimension, we can look at a hill, see someone at the top of a mountain, for example. But we are incapable of seeing anything in the 4th or 5th or 6th dimension because we live in the 3rd dimension. So mathematically, we've got a problem. Mathematicians have worked out formulas to figure out distances in dimensions that no human being can physically see. And this formula is basically the one they use. Now, we don't have to know this formula, but it is nice to know what's going on. And ACL has this built into the background, right? It calculates the distance in the background. And mathematicians have obviously proven that this formula isn't just a thumbsuck, that it is actually valid and that it does actually work for other dimensions. And your average formula is basically in 1 dimension, I'll just take the numbers, divide them by how many ever there are. 2 dimensions, take your x values, add them together, divide them. Okay, I know what I did wrong now with my other calculation. I will go back there now. These are my formulas. So let me just go back a bit here. Okay, let's see, it helps to be awake when you're teaching a bit of mathematics, right? So when I was trying to work out the averages for you earlier, okay, I was trying to work out, let me just find this cluster, all right. I was trying to work out the average of this cluster, for example. The x value here is 1. The x value here is 2. 1 plus 2, average, I need to add. I was subtracting, sorry. 1 plus 2 is 3. 3 divided by 2 is 1.5. There's the average. Y value, 3 is the y value here. 1 is the y value there. 3 plus 1 is 4. 4 divided by 2 is 2. How difficult is it to work out an average when you're awake? Eh? When you're asleep, it's impossible. So that's how you work out those averages. You just add the x values, divide by the number of items in the cluster, and so forth. Okay, so let's go back to where I was. I feel a bit better now. Okay, so let us see. Where are we? All right, let's skip this. Okay. Right, so there are our different formulas. Okay, so this question, one of the questions I had was, where do I put my cell phone towers? If this was, you know, what these zeros and ones and everything else meant, whether I'm working in 1 dimension or 2 dimensions or 3 dimensions or 10 dimensions, right? So let's go back to my simple example with houses in the same street. Remember, I thought initially, oh, maybe because of these clusters, I'll put a cell phone tower there near house number 1 because it's kind of in the center of that first cluster, but another cell phone tower maybe near house number 7 because it's in the center of that cluster. But is that such a wise idea? Because imagine I built cell phone towers there now, and some new people move into the neighborhood. They build houses in location 3 and 4 where there aren't cell phones at the moment. Now what? What do I do? Because they might not be in the optimal position anymore, and it's very expensive to go just move a cell phone tower. So maybe when I'm thinking about this the first time, I should say, wait. There are empty stands as well. I should maybe take them into account. So maybe what I could do is I could put into ACL 0, 1, 2, 3, and 4 as data points, even though there are no houses at 3 and 4 at this stage. And then run the algorithm from the beginning and get a different data point, a different centroid. And then I'll get these clusters maybe. Or maybe I could try something different. I could do what is called normalizing the data. Now, normalizing the data means that somehow you change things slightly. So on my map or in my diagram, there's a house in position 0, 1, 2, and I can kind of adjust it and say, okay, even though there isn't a house in position 3 or 4 at the moment, let's on the piece of paper, shift the houses a bit maybe further to the right so that they take up more of the space in the land, including the empty land. You can't physically move the houses in the real world, but maybe I can move them to the right somehow on the map so that I can do this. So I'm normalizing the data in that way, making things comparable, making the empty spaces almost comparable to the houses in a manner of speaking. So what is this normalizing data? How do we do it? Now, we often normalize data in the real world. When you have centimeters and kilometers, I cannot add centimeters to kilometers. I cannot compare centimeters to kilometers. There are different units of measurement. I've got to normalize them. I've got to convert them into the same unit of measurement. I've got to say, take centimeters and change it to kilometers, or change kilometers to centimeters before comparing them or before adding them and so forth. And so normalizing data is just, I need to somehow make data comparable. Now, this is important, not just in the cell phone example, but again, in my example with fraud happening at a certain time of the day. Suppose we were not aware that fraud is more likely to happen after, or let's say we were not aware that transactions that happened after 7 in the evening are more likely to be fraudulent. Let's say we didn't know this trend. How do we, if we import data into ACL and say, these are the transaction values, and these are the times that you place, how do you logically link, mathematically speaking, a time to an amount? You don't. They are two different things completely. A time is not the same thing as a transaction value at all. There's no mathematical connection. They are completely different units of measurement. They're measuring very, very different things. It's not even like centimeters and kilometers that still at least measure the same distance. Time and money, they measure two different things completely. So, there's a saying, you can't compare apples to oranges. Well, actually, with normalization, the point is I need to compare apples and oranges. I'm going to change the oranges so that they become apples or vice versa. I'm going to change the times and the amounts into some comparable units or something that somehow works together. That's normalizing. Now, there are two ways built into ACL Web to normalize data. One's called standardization. One is called scaling to unit length. Now, I'm not going to go into it here. You can go read about it, learn about it if you want to. It's a whole mathematical thing, right? It's a long story. Here, for those of you who are interested, these are the formulas. Standardization uses z-scores, and there's a formula x minus x bar, so the mean of x over sigma, the standard deviation. Scaling to unit length uses the norm of a vector. Those of you who know about vector spaces and that know what a norm of a vector is. If you don't understand this is fine, okay? But understand there's a lot of mathematics behind K-means clustering, a lot of it. So this makes it quite difficult sometimes for clients to appreciate what's going on when it comes to normalizing the data. It's very difficult to understand, to figure out how do you change a time into a number that is comparable to a dollar value, which is comparable to a branch, and how do these things work together? So it helps to know the maths. So it's going to be, but it's not absolutely essential. Just be very careful. If you don't know the maths, you've got to be very careful how you interpret the clusters. You might learn something. If you do know maths, it helps, but you've still got to be careful how you interpret what the clusters are that ACL gives you. All right, so you can see it's complicated. Now, there are other ways, not in ACL, of normalizing data. This is a formula, one of many that you can use. I'm not going to explain it. You can go Google it and see when it might be suitable. But this formula, I can tell you, has something to do with scales. Like if you have a scale of 1 to 10, 1 is bad, 10 is good. This is not comparable to a dollar value or to a time of the day or to a month. So this somehow normalizes it. It makes it comparable to certain other things. The reason I'm showing you this formula is to let you know there are other ways of normalizing data that are not built into ACL. And you might decide that once you understand all the maths, that a certain data set does not lend itself to standardization or the unit vector method to normalize things. You might decide this formula or some other formula you found on the internet is better for normalizing things. So go and Google. If you want to do this for real, you've got a lot of mathematical research to do, a lot of mathematical learning to do. All right, so when do we normalize data? Well, if I have a scenario where the stands are empty, or if you think about that, so for an example, I put the numbers evenly spaced on the number line. But what if house 0 has a very big yard? The distance from house 0 to house 1 is much bigger than the distance from house 1 to house 2. So I shouldn't actually be saying place a cell phone mast in a certain cluster when the distances are very different from one house to the next. I should take this into account. So I should make the distances somehow the same or somehow comparable. When we have independent variables, variables that are not related to one another, as I said, what is the connection between a time and a transaction value? What is the connection between a transaction value and a branch and a person's name and employee number? There's no connection. These things are completely independent. So you can't spot a cluster if they're completely independent. We need to make them comparable. We need to make them somehow dependent. So, we can't now say I've got 100,000 and I've got a time 10 a.m. Now 10 a.m., by the way, I can theoretically easily turn into a serial time. So that becomes 0.416. But now I've got two mathematical numbers now, 100,000 and 0.416. But if you subtract them because you're trying to work out a distance, if this is one-dimensional, if it's two-dimensional, you're still going to get a very big answer. Right? But the difference is going to be huge. So if the difference is huge between these two, it's going to impact your cluster. Do you really want to subtract these two things? It becomes a nightmare. Your clusters are going to shift all over the place. All right, the clusters will be distorted. So sit down and think about what I've said. This is a bit tricky to understand, but it's important that you understand this. These things are not comparable yet. So I've got to figure out how to make them comparable. I've got to figure out the appropriate way to normalize them. All right, now, supposing after lots of research and agonizing and thinking, I decide that I want to normalize this in ACL using standardize. So I want to go and use only one dimension, only one street. So I'm going to use my data points column, and I decide to choose standardize. Now notice in other fields, I have chosen something else for the first time. I've chosen data points. And this is the result I'll get, depending on my settings and which centroids were chosen randomly the first time. So there are two clusters here, C0 and C1. Now notice I've got these strange looking points, negative 1 point something, 0.66. I can tell you none of those exist in that data. Remember the data I had 1, 0, 1, 2, 5, 6, 7, 8, 9. Those were where the houses were. None of these values physically exist on my map. None of them exist on that number line, not where none of those houses exist in those positions. These are the normalized, the scaled points, the modified ones. And ACL used these to determine the centroids, the clusters, and so forth. Now, if I hadn't chosen, let me go back. If I hadn't chosen to see the data points in other fields, what would happen is I would not see this last column. I would see only the modified, the normalized data points. So I would see those first three columns and I would say, okay, I can see where the clusters are, but which of the houses belong to which cluster? I don't know. I can't tell you if I look at that. Those mean nothing to me. They mean something to ACL. So I would, however, if I add this original column, I could say, okay, the normalized one, that one was originally 0. ACL normalized and made it negative 1.5. Fine. The point is I can see 0, 1, and 2 belong in that cluster. So it helps me to add in the original data so I can see what's going on. So clustering, the idea is a good one, right? ACL divides the data into groups, into clusters, using mathematics. So it doesn't have any of our human bias, which is good because then we can look at the clusters afterwards and provided we can make sense of them and find an explanation for why those three houses, those three transactions, those three whatever are in the same cluster and not in the other one. Once we can find something in common with each of the elements in the cluster from a human point of view, from an order point of view, we might learn something we didn't know before, okay? But mathematically, there's a lot of things going on in the background. And we don't have to know it. We can use clustering without it and see what we can figure out from here. But it obviously is better to understand the mathematics, especially when it comes to normalizing the data. When you're trying to compare apples and oranges, there are different ways of normalizing the data. There are only two built into ACL. There are lots of methods out there to normalize data. Which one's best? Well, if you want to know that, you've really got to go dig and do lots of research, lots and lots and lots. Now, my advice is don't go to a client and say, we're going to do this for you. Explain to them if you really want to how this works. Let them figure it out on their own. Let them play with it. It is very, very, very tricky. My advice wouldn't be to say to them, I'm going to script this for you. Don't do that. Because if they come up with clusters that are useless to them, they blame you. If they don't know how to interpret the clusters, they blame you. So you can teach them if you really want to how this works, but make sure they understand the complexities so that they understand they are ultimately responsible for figuring out all these settings and for interpreting what's going on in their clusters in their environment. Okay, so right. When we try and find clusters, we've got to decide how many iterations do I want to do. Should I do this once or twice or 3 times or 10 times? Now, with my very first simple example in the street, when I did this manually in PowerPoint, I realized if I did it a 4th time, I would be wasting my time. It converged already after 3 times. But in the real world, it might only converged after 20 times. So how do I know the correct number of iterations? So let's suppose we have some data and we have done some testing on this data. We tested the clusters after doing 1 iteration, after doing 2 iterations, after 3. So, okay, sorry, not after iterations. I want to know how many clusters I should choose. So I chose 2 clusters, right, in my examples in PowerPoint. But should I choose 2 clusters in the real world, or 1 cluster, or 10 clusters? Now, 1 cluster obviously wouldn't make sense because everything's in the same thing. So what happens is, if let's say we've got a data set and we've chosen the setting 1 cluster, and what we get is a distortion. In other words, the different data points are very, very far, let's say, from the centroid. Okay, so the distortion we calculated for argument's sake with 1 cluster was 1.5. Then we tested it, let's say, and said, okay, let's create 2 clusters. So we have 2 clusters, and we test that, and we discover the distortion is close to 2. That's much better than a distortion of 3.5. So 2 clusters is better than 1 for this data set that we haven't actually seen, right? But let's pretend we've seen it. Now we test it with 3 clusters. What if I take the same data and divide it into 3 clusters? Oh, the distortion is only 1. Looks like it's getting better. And we notice the more clusters we have, the less distortion we have, which makes sense. Your clusters are getting smaller because you have more centroids. So you're not getting a, you're not going to have outliers being very far from a certain centroid. Now you might think, oh, okay, well, the best based on this diagram is to choose 9 clusters, but actually that's not true. Look at your return. Every time you introduce a new cluster, it takes longer to process. You got a very good return here. Your distortion dropped dramatically from 1 cluster to 2, dramatically from 2 to 3. It dropped only slightly from 3 to 4, and even less from 4 to 5. So it keeps dropping, but the distortion drops very slowly. So we use what's called the elbow method. If you could draw a graph of the distortions, you would see, if you imagine this was a human arm, where would the elbow be? The elbow's there. So the optimal number of clusters for this particular data set, this fictitious one that we haven't seen, is 3 clusters. Now, obviously, there are formulas that you could use to go calculate this, or you could go write, script to calculate this and so forth to figure out how many clusters there should be. And I'm not going to do that. I mean, that's a whole exercise, but that's a whole mathematical thing again, right? Based on all sorts of things, what's the optimal number of clusters? So before you even touch the machine learning, if you want to know how many clusters to choose, you've got to go write a script to calculate this optimal value, calculate where the elbow is. So you understand how complex this can actually be if you really want to get into it. So as I said, clients can use this without getting very complex, but they must understand that the clusters they get may not be great. They might get lucky if they are able to interpret why certain things are in a certain cluster. They might draw benefit from it. If they want to get really involved, they can. I don't see most of them getting involved in that depth, but they really can dig into the maths if they absolutely want to. And they can get heavily involved in the scripting if they really want to. But that is basically clustering. Now, cell phone towers is the example I used a lot. But remember, as I said, it's not always physical distance. Any data that's suitable can be used. Some areas of application are for fraud detection, things that cluster together. And when we look at them, we go, but why are they together? And we realize there's something strange going on. There's fraud. It helps us to get a feel for the data sometimes. Instead of using your stratify command and your normal commands in ACL, you can see clusters and go, okay, it's unusual. Certain clusters at certain transaction values for certain products at certain branches, certain things always happen together, in a certain way. I wonder why. And you start getting insights into the data. You can analyze expenses by and across branches. We know we can do this for summarizing, cross-tabulate, and so forth. But we might not have seen certain clusters using those methods. Remember, we have our bias. We look for specific things. We tell ACL, I want to summarize by branch and by expense. When you use clustering, it doesn't, you can't tell it, I want you to use exactly these things in this order. It takes everything you've given it and it figures out where it wants the clusters to go, right? You can sometimes look at keywords. Do certain keywords often occur together? So whenever we buy from supplier ABC, do you often see the words pens, pencils? Are there certain keywords? Now, ABC is a stationery company. This is not surprising. But if there's something untoward, strange keywords are used to mask certain activities. You've now trigged onto the fact that there are certain suppliers where certain strange keywords are always there with the payments and the invoices. Go and investigate. Right. Audit applications, yes, there's the fraud detection. You might decide you first want to find fraud using standard means and then use clustering on that to see what patterns you haven't spotted. Remember, clustering is there to create groups without our bias. And then we look at it, we might be able to spot trends that we never thought of. Sometimes you might say, well, fraud detection, let me first find the clusters instead of finding the fraud. And then when I find unusual clusters or outliers, these clusters that seem to be very different from the others, let me go look at those specific clusters for fraud. Now, here's a question. Should I include employee numbers when we do our analysis, when we're looking for fraud? Well, often we would say yes. You want to know if an employee is processing the same thing. But there's a problem, right? Is an employee number, comparable to a transaction value? The answer is no. Can you normalize it? Well, that's a whole nother debate, right? So maybe you don't want to include it, right? So when you want to get a feel for the data, as I said, you can use stratify, but it's biased because you are deciding the ranges and the groupings. Clustering is unbiased. You can analyze expenses by and across branches, but branch codes are not natural, normal numbers. They're very artificial. So you're going to get these wrong, distorted clusters. So what do we do? Maybe we could say, well, make them ridiculous numbers, so separate them. So branch A is 1 and branch B is 100. But again, why? What's the difference between saying branch A is 1 and branch B is 2 versus branch A is 1 and branch B is 100? Maybe there's a different way. Now, do you understand the challenge here? I want to use branches. How do I turn a branch name or branch code into a number that is somehow comparable, that makes sense with other things? And this is something you'd have to sit and think about. You'd have to get creative with it. You would have to also test it out. So this is not an exact science. If any client thinks this is an exact science, you need to educate them. It's a complex business, this. It's a really complex business. So it can be helpful, but it's complex. And again, the clusters we get, if we can make sense of them, great. If we can't, it's back to the drawing board. All right. Audit applications, some more. As I said, check if certain keywords appear together. Now, what do? Should we assign a keyword a value? So should we say paper is 1, pens is 2, computers is 3? Or should we say, okay, wait, papers and computers and pens and computers are very different items with different prices. So we'll have 2 dimensions. We'll say paper has code 1, pens 2, pencils 3, they close together. Computers, printers will also have a separate dimension for those because those are more expensive items. Now, is 1, 2, and 3 natural in the sense of there's some logical link between paper and the number 1? No. So should we number it this way? Well, that's debatable. So now you get into a whole discussion in the office or a debate with yourself. Should I do this? And if you're not sure if you should or not, try it. Just try it. That's the only way you're going to figure out eventually what to do. I would like to say to go to the internet and see what people have done out there, right? Unfortunately, at the moment, there's almost nothing on the internet in terms of how people have standardized things, and or not standardized, normalized things. I can tell you that there's one example that you keep coming up with, that you keep seeing on the internet over and over and over, but it's about the only one. So you're going to have to try a lot to play with this different standardization. If you manage to get hold of client data, obviously you can't distribute it to anyone outside your organization, but try just for your own sake to see what's going on there. The challenge with using client data, of course, is if you don't know their processes and policies and procedures intimately, it's going to be difficult for you to decide what to use to give to ACL as these dimensions, as information, as data. It's going to be difficult for you to interpret the results. All right, now, again, when it comes to using keywords, should I maybe say, okay, I want to see if there are similar keywords or related keywords like cab and taxi. Now, how do you turn cab into a number? Should I, for example, say the letter C I'll represent with a 3 and an A with a 1 and a B with a 2. So 3 plus 1 plus 2 gives me a score of 6. Now, the problem with that is you get a lot of words that will add up to a 6. So is this a good idea, bad idea? How do I change a keyword into a number? There's nothing inherently mathematical about a word. So you see, this is one of the challenges, but people can see how keywords cluster together if they are very careful in their design of how to change a keyword into a number. All right. If we do use values for each word, we can cluster them with similar scores, and maybe we'll see, oh, everything in this cluster, these are abbreviations of the same word or variations of that word. We have to draw the conclusions. We have to know what these, data point values of 1 or 6 or whatever it is refer to. We've got to keep a document somewhere to say 6 refers to the word cab, for example. 8 refers to the word taxi, whatever it is. So you've got to be very careful with this. It's very tricky. It's interesting, but it's complex. It's really complex, and it's really tricky. Okay, so when can we use machine learning? Yes, good question. Well, firstly, you can only use it with numeric fields. All the fields that you give to ACL must be numeric. So even if you decide you can give it branch codes, let's say you decide that, rightly or wrongly you decide that, you must import those branch codes as numeric. They shouldn't be artificial. An employee number is artificial. They need to be natural, so to speak. But we've got a problem. What if we want to include employee numbers in our analysis to see if there's a trend there? You might have to say, well, ignore employee numbers, we'll find patterns without it, then afterwards see with conventional methods if we can, if things in a particular cluster always come from the same employee. On the other hand, you might find a clever way of changing those employee numbers to something that's supposedly more natural. Okay, 925 is not numeric, but you can make it numeric, make it a serial time. But of course, is it comparable to other things? So variables, everything in that table that you use, all the columns you're going to use to give to ACL's machine learning, to its K-clustering, have to be comparable. You have to be able to compare apples and oranges, normalize them. And what happens is machine learning is useful if you are looking for patterns, but you're not sure what the pattern is that you're looking for, right? This is not like train and predict. With train and predict, you know what the inputs are and you know what the outputs should be. And you just need ACL to figure out the formula. With K-means clustering, what happens is you know the inputs. Well, you're not entirely sure, to be honest, what the inputs are. You just know there are transaction values, there are supplier names, there are times. That's as close as you know about inputs. You don't know what the answer should be. You don't know what you're looking for, what patterns. There's no answer. So you're saying, ACL, here's a bunch of data. Tell me something I don't know. Now, it doesn't really tell you something you don't know. It creates clusters. You've got to go look at each and see if you can figure out from there anything that you didn't already know. Okay. Now, K-means clustering we also use only when we do circular clustering. Now, what is circular clustering? That's what I did in this presentation, where we kind of drew ovals or things reasonably close to circles around points. You have a problem if you have data where the correct cluster, let's say, starts on one end of the Cartesian plane and extends to the extreme other end. Now, you don't really have something resembling a circle. That's more resembles a sausage. So K-means clustering won't work for that kind of scenario. You must know what variables you need. Now, this is a problem because we are trying to find out what we don't know. So how do you find out what you don't know when you're not actually sure? Yeah, if you don't know what you don't know, so what information do you need to tell you what you don't know? So what variables do you need? I don't know. This is tricky. So you can say, I think it makes sense to have transaction values. I think it makes sense to have employee numbers. You might be thinking right. You might be thinking wrong because you're not sure what you're going to find out. You are saying to ACL, tell me something I don't know. And to get there, I'm not actually sure what the variables are. So you've got to try and put things in there. You're not going to do it completely blindly. You're not going to put in there everyone's favorite color as per one of my silly examples earlier, because someone's favorite color does not impact if they commit fraud or not. So that would be a completely silly thing to put in. So you have some logical guidance, but again, you're not sure what the inputs are. So it's a bit of it's a guessing game, and ACL works with the class, creates the clusters for you. Look at them, see what's in common in each cluster. And from there, you might learn something. So it is useful, but it is very tricky and it is very complex. Well, that's it for K-means clustering. Yes, take a deep breath. Watch this presentation 1,000 times, get line data, invent data, play with this, test it, read up on it, go watch videos about the different types of normalization to understand it better. But my advice is don't go and make this a major selling point if you're in sales of ACL, because it's going to come back to bite you legally if you produce something that's a lot of rubbish or that produces meaningful clusters only once and never again. So be very, very careful about what you tell clients when you sell this. Okay, so that's it for this video. I hope it helped. I hope it helped to confuse you a bit. Not really. It will confuse you. It confused me the first 1,000 times, and it still confuses me sometimes, right? But please go look at this. It takes a long time to get used to. Right, have a good day.